Using the definition of the definite integral, let's say we were interested in finding the area between two curves. So let's say we have for xy plane, we have one curve here, let's call that f2 of x. And let's have another curve at the bottom and call it f1 of x. Now what happens if we want to find the area between those two curves and between the interval AB? So we just want to find this area. Well, it makes sense that if we find the area beneath f2, that's going to give us the whole area including this chunk at the bottom here. And if we find the area of f of 1, then that's just going to give us this area here. So it makes sense that to find this area between them, we just need to subtract the area underneath this curve from the area underneath this curve. So that's the definition of the area between two curves. So the area between the two curves is going to be equal to AB of f2x minus f1x dx. And just to show you an example of this, let's say we have the function, the two functions actually. We have the function y equals to x, and we also have the function y equals to x squared. And this is the area we're interested in. So let's say that we want to find the area between 0 and 1. So if you set the equations equal to each other, you will find that they intersect at the point 1, 1. So we want to find this area here. Alright, so how do we go about doing that? Well, what we need to do here is we're going to first of all figure out which is the function that is at the top and which one is at the bottom. Here, this function x squared is actually at the bottom, so that one is going to be f1. And the function at the top is actually the straight line of y equals to x. So the area in this case is going to be 0 to 1 of the function x minus x squared dx, and this is going to be equal to x squared over 2 minus x cubed over 3 from 0 to 1, and this is going to be 1 over 2 minus 1 over 3. And the second part we can ignore, because if we put 0 in here, the whole thing becomes 0. So in the end, we're going to end up with this is equal to 1 over 6. And that's the area between those two curves and within the interval 0, 1. Now let's do another example. Let's have the functions x and the function 3x. And let's say we want to find the area within the interval 0 and 3, and we want to find this area here. So that's the area. Now just to give you a visual representation of what we're going to be doing, I'm going to find the values here of intersections. So those two values here, this one is going to be, well, what's the value of this function when we put 3 into it? That's just going to be 3. And this is not to scale, by the way, so just ignore this for a second. This is going to be 9, because if we put 3 into x squared, 3 into 3x, that's going to be 3 times 3, that's 9. And then that's what we're going to have. So what's the area of this? Well, the function at the top is 3x and the bottom is x, so we're going to have area equals to integral from 0 to 3 of 3x minus x, which becomes 2x. And once we integrate that, that is going to become x squared, because the 2 at the bottom is going to cancel out with the 2 at the front here, from 3 to 0, and this is going to be equal to 9. So the area between those two lines is equal to 9. And you know, well, 9 units squared, depending on what units we choose for dimensions here. And you might say, well, I don't actually believe you. That doesn't look like it would be 9 units squared. I mean, how can we prove that geometrically? Well, let's have a look at this. First of all, let's calculate the area of this triangle. So the triangle here is going to be half base times height. So the base is 3. So the height is also 3. That's going to be what? That's going to be 9 over 2, which is 4.5. Now, what's the area of the bigger triangle? Well, that's going to be height is 9, base is 3, so that's going to be half of 3 times 9. So 27 over 2, that's going to be 13.5. And now to get this area, we're simply going to subtract the bigger triangle from the smaller triangle. So this minus that, what's that going to be? That's going to be 9. So that's a really nice thing about definite integrals, that it allows you to do a lot of things. And you might think, well, why do we need to find the area of something? Well, you might be interested in it if you're working with something that needs to have symmetry of some sort. It might be related to a structure, it might be related to something that you're designing. So that's why this is quite important. And it can also be used in a lot of different contexts, which we will explore in a few videos later on. But this is basically the general idea behind finding the area between two curves using definite integration. And in the next video, I'm going to discuss how to use more of the numerical approximation that we used in the last video, which was a Riemann sum, to find the area underneath a function or curve, and how that approximation increases in accuracy with increasing number of rectangles.